This slide is about the graphical and mathematical description of waves. Before we look at the waveform and equations here, let's think back to chapter 14 when we looked at simple harmonic motion. In that chapter, we had the position of a mass on a spring was equal to, was a function of time and was equal to the amplitude times the cosine of omega t, was one way we wrote that, and the mass could only be at one position at any instant of time. But waves are spread out, and so they actually are a function of two variables, the position x and the time t. So it makes the equation a little bit more complicated. And here it's written in terms of the wavelength and the period. Down here I have an alternate description where I've written it in terms of k and omega, where k and omega are equal to those parameters there. I think this is a little bit better way of writing the equation than the one up here. So we will use both of these. Also, the relationship for velocity, I think we've seen that before. If not, it's the wavelength times the frequency gives you a constant for the velocity of the wave. Something else to note about this formula here, it says this is a formula for displacement of a traveling wave moving to the right with amplitude A, wavelength lambda, period t. This minus sign here means the waveform is moving to the right. If this sign happened to be a plus, the waveform would be moving to the left. So that's something you need to note there. Also, now let's look at the waveforms. This one is shown as a cosine wave, and as I've written over here, the waveform could also be drawn as a sine wave, so it could be a sine or cosine wave. We still have the period is the length of time for one wavelength, or one complete wave, and the wavelength is the length of one complete wave. Also note here on these waves, this wave or graph is y versus t, so it's the y position versus time. This wave down here is y versus the x position. So this first wave here would be taken at x equal to some value, say x1. And this waveform down here is y versus x at t equal to some particular time, say t1. And another note here, you might wonder, how does velocity end up being meters per second when you have this product? Well, you might recall the relationship between the period and the frequency. The frequency is equal to 1 over the period. So if you rewrite this formula, you can write it as wavelength over the period. Wavelength would be in meters, time in seconds, so you do get units of meters per second. When you show it like that, it's a little more evident. This slide is on sound, and then the next slide is on light waves. So on sound waves, as we had before, the loudspeaker cone moves back and forth, shown here, and it creates regions of higher and lower pressure that we call compressions and rarefactions. So this would be a compression, and this is a rarefaction, compression, and so on. The compressions show up as the peaks on our waveform. And notice what they're plotting here for a sound wave. They plot pressure versus position x. And this line is the atmospheric pressure. So the sound waves then alternate around the atmospheric pressure. And then we also said that the speed of sound varies with the medium, and it still follows this formula for the speed. The medium, if it's in air, we had a formula for that. But then if it's in a liquid or solid, we mentioned that generally sound travels faster in solids than liquids and faster in liquids over air. And here are some hearing ranges for a variety of living things. And notice that the human, we're in this category. And then all of these we call ultrasound. Its frequencies above our hearing range, so they have shorter wavelengths and they can sense smaller objects. So for instance, you look at a bat with this frequency being so high, they can sense smaller objects, and so they can sense bugs in the air to catch. And if we look at this relationship, the speed of sound in air is fixed due to the temperature, and then so if the frequency goes up, the wavelength has to go down to maintain this constant speed in air. And the smaller the wavelength, the smaller objects they can detect. So that's how that works. We will talk some more about how we hear in a later slide. But what happens is, as the sound hits our eardrum vibrates, and that's how we hear the sound. And then also with ultrasound here, the ultrasound wavelengths travel through our bodies, and that allows us to make images of the body's interior. So you might be familiar with ultrasound for our bodies. Well, let's now talk about light waves. Light is an electromagnetic wave. Let me try this again, see if my pen's working. Light is a type of an electromagnetic wave, as we've mentioned before, and it can travel in a vacuum, or it can travel in a medium like air or other things. And although there is a slight difference between the speed in air and a vacuum, we ignore that small difference and just say it approximately is the same at 3 × 10⁸ meters per second. So what we see here in this graph is a spectrum for the electromagnetic waves. It starts down here at AM radio, and you can read, goes to FM, TV, microwaves, infrared. The visible part of the spectrum is only this small part, and you might be familiar with the colors here. We use a little acronym, ROY, G, BIV, to remember these colors: red, orange, yellow, green, blue, indigo, violet. And then electromagnetic waves also follow this formula of the speed equals the wavelength times the frequency. C is reserved for the speed of light in air or a vacuum. If the electromagnetic wave is traveling through, say, clear glass, we would still use the formula V equals lambda F. It slows down, but we still use this form of the formula here. Waves transfer energy from one point to another as they travel. So on this slide, we want to look at the energy and something called intensity of a wave. What they show here is you have a source of power, and it's considered to be a point source. So you can think of it maybe being a light bulb or a speaker, and the wave transmitted makes concentric circles. They show this as a cross-section of a spherical wavefront. So think about a small balloon, and as you blow it up, it gets larger and larger. That's sort of what they're showing here with these concentric spheres representing the waves. And as it goes out, you can see there's a radius here, R1, and then it gets bigger, some radius here, R2. And it says the intensity, I1, is at R1, and then the intensity I2 is at I2. So what they're telling us is that as you get away from the point source, the intensity is going to be getting less and less. So it says the energy from the source is spread out uniformly over a spherical surface that has an area of 4 pi r squared. So it says as the waves spread out, so does the energy of the wave. The intensity decreases as r increases. And here is the formula we use to calculate that. You might remember that power is equal to energy over time. So this is equal to joules over seconds, and the unit for power was a watt. So 1 watt equaled 1 joule per second. So what we're doing down here is we're taking power, which is in watts, and dividing it by meters squared. So that's what we mean by intensity. It's so many watts per meter squared. And this formula now only works for spherical surfaces because the denominator is the area of a sphere. So keep that in mind. Intensity in general would be power over some area. So we don't always have to use a sphere. We can use other areas to calculate the intensity. So the power here of a wave is the power is the rate of energy transfer with respect to time, but intensity is the power over some area. One other thing I wanted to mention about this slide is we can represent the waves here in a different format. Well, actually, let me not draw it that way. Let me just draw it like this. If you have a wave going along like that, these lines represent wave fronts. So, for instance, if I drew a line at the peak of these like that, this represents one wavelength, and this would represent the peak. Well, they're doing a similar thing here, only the waves are spherical. So the distance between the two waves here, you could think of as being one wavelength, like that. So these are called plane waves, means they're so far away from the circles that the waves flatten out, and you can show them as just being straight lines like that. So this is called a plane wave when we represent it like that. That would be all for this slide.